Hello students. After discussing the failure of wave theory of light to explain the observations from experiments on photoelectric effect of the chapter Dual Nature of Radiation and Matter, we had seen the important phenomenon which is said to be a work function and is to be defined as the minimum energy required to free electron from a given surface is called photoelectric work function, denoted by phi0 of the material of the surface, and the value of the work function for a certain material is same but is different for the different material. We had started with the Einstein's postulate of quantization of energy and the photoelectric equation, and here in this Einstein's postulate we come to know that under certain conditions light behaves as a particle, and hence the energy which is to be released or absorbed in bundle or quanta, this energy of light is to be known as photon, and hence the energy of the photon is to be given as E is equal to h nu, where E is the energy of the particle and nu is the frequency of incident radiation. H is the Planck's constant there, as Einstein's had extended the Planck's hypothesis to give this relation, which is to be known as Einstein's relation, and this Einstein's relation gives the relation between the particle-like property, that is energy, and wave-like property, that is frequency. Last time we had started the explanation using Einstein's postulate of quantization of energy for the observations from experiments on photoelectric effect, and in the last lecture we had discussed about the photoelectric equation, where it is to be determined. Einstein's first of all had used his postulate, like when a photon is to be incident on metal surface, it will be collide with electron, and hence all energy of this photon is to be absorbed by electron there. This absorbed energy will be utilized for two purposes. Some amount of energy will be utilized to leave the surface of the material, which is to be called as the work function, and remaining amount of energy will be appear as a kinetic energy of the emitted photoelectrons. And hence by using this, the equation is to be given by the Einstein, which is to be known as the Einstein's photoelectric equation, and is given as maximum kinetic energy is equal to h nu minus phi 0, and after that we had determined the value of the work function phi 0 there. As we are decreasing the value of the kinetic energy, frequency is also decreases. We had made the kinetic energy 0 and the frequency of the incident radiation will reaching at the value threshold frequency. By considering these values, the Einstein's photoelectric equation comes as 0 is equal to h nu minus phi 0, and hence the value of the work function can be determined, that is phi 0 is equal to h nu 0. And finally Another form of the Einstein's photoelectric equation can be written as maximum kinetic energy is equal to h nu minus h nu 0. By using this Einstein's photoelectric equation, last time we had seen the very important aspect of the photoelectric effect. As we know that to observe the photoelectric effect, the incident frequency must have greater than threshold frequency, and it is to be explained by using the Einstein's photoelectric equation, that if the incident frequency here is less than threshold frequency, then the photon will not have enough energy to liberate the electron, and hence as electrons are not emitted from the surface, the photoelectric effect cannot be observed and photoelectric current is not flowing over there, whatever will be the intensity of incident radiation. And from the same equation it is clearly explained that if we are taking the incident frequency is greater than threshold frequency, then we are getting the positive value of the maximum kinetic energy. That means the electron having the sufficient energy to overcome the metal surface, and hence the photoelectric effect can be observed. Now let's proceed the explanation for all the observations that we have seen already for the photoelectric effect by using Einstein's postulate of quantization of energy and Einstein's photoelectric equation. Now, according to the Einstein's assumption, if the intensity of incident radiation is increased, number of energy quanta of photons incident on unit area in unit time is also increased. Now, this can be understood by considering the same diagram of the process of photoelectric effect. As we know that when the incident radiation of suitable frequency incident on the metal, electron absorbs all of its energy. Okay. According to Einstein's assumption, when the photon is to be incident on the material, electron will be absorbed all of its energy, and hence after that the electron is emitted from the surface. Here Einstein's assume that if we are increasing the intensity of incident radiation, that means here we are increasing the number of energy quanta, or which is said to be a photon, which is to be incident on the metallic plate. Increasing the intensity means we are increasing the number of photons incident on the material plate. For example, over here, if the intensity is low, containing only one photon, so that this one photon will be collide with one electron only, and hence only one photoelectrons will be emitted and the current will be very low. If the intensity is to be increased, hence we are increasing the number of photons there. Now consider that the intensity is to be increased by increasing 2 photons. So obviously these 2 photons will collide with 2 electrons from the metal, and hence 2 photoelectrons are to be emitted. And here we can say that the number of the photoelectrons in this case, as we have increased the intensity, the number of photoelectrons are also increases. Similarly, as we are increasing the intensity more, if we are considering 3 photons are to be incident on the material, so it will give the result that 3 photoelectrons are to be emitted from the surface. And hence, we can say that increasing the intensity of incident radiation means increasing the number of photons incident on unit area in a unit time, which gives the result in increasing the number of emitted photoelectrons. And hence, we can say that the larger intensity radiation will knock off more number of electrons from the surface, and hence the current will be larger. Again, the condition must be satisfied that the incident frequency should be greater than threshold frequency. Conversely, we can conclude lower intensity implies less number of the incident photons, hence less number of ejected photoelectrons, and therefore lower the current. So by using this Einstein's assumption, here we come to know one of the observation from the experiments on the photoelectric effect, that the photoelectric current is directly proportional to the intensity of incident radiation. As we are increasing the intensity of incident radiation, the photoelectric current is also increases. By using the Einstein's postulate, here it is very clear now. Increasing the intensity means we are increasing the number of photons, which will be increased to the number of electrons ejected from the metal surface, and hence the current is also increases. Next is higher the accelerating potential, more will be the number of electrons reaching the collector plate. Over here, once the electron is emitted from the surface, okay, and if the collector is at the higher potential than the emitter, then the electric field will accelerate the electrons towards the collector. Just recall the experimental setup when the collector plate is to be placed at the positive potential, and hence when the electrons are emitted from the emitter plate, the photoelectric current is to be shown in the microammeter, and that's why we can say that all the electrons are attracted towards the collector plate. So over here, the electrons which is to be emitted from the surface, it will be collected by the collector plate if the collector is at the higher potential than the emitter, because in this condition the electric field will accelerate the electrons towards the collector, and that's why we can say that higher is the accelerating potential, more number of the electrons reaching the collector plate over there. Hence, number of electrons reaching to the collector plate is more, we can say that the photocurrent is increases. The photocurrent I will be increased with the accelerating potential initially. That the same can be shown over here. As the accelerating potential is to be increases, photoelectric current is also increases initially there. Okay, here we had kept the collector is at the higher potential than that of the emitter plate, because of which more number of the electrons reaching the collector plate, and hence the photoelectric current is increases there. Since the intensity of incident radiation determines the number of photons incident on the metal surface on unit area in unit time, it determines the maximum number of electrons that can be knocked off by the incident radiation. Hence, for a given intensity, if for example here we are considering the intensity only I01, so for this given intensity only, over here when we are increasing the accelerating potential, the photoelectric current is also increases. Okay, and this increase will be there till a particular limit for all the electrons which will be knocked off from the surface, and it will be reaching to the collector plate. Further, there is no increase in the photoelectric current is seen beyond a particular limit, and hence here already we had discussed this thing which is to be known as the constant value of the photoelectric current we are obtaining is said to be a saturation current. So here the Einsteins explain the concept of the saturation current in the photoelectric effect also, and hence we can say that as per the Einstein's postulate, if the incident intensity is to be increases, it will increase the number of incident photons, and hence the saturation current is also increases. Now, as per the Einstein's postulate, when the energy is given by a photon to electron, as soon as the radiation is incident on the surface, there will be the exchange of energy between photon and electron takes place very instantaneously. Hence, there is no time lag between the incident of light and emission of electron. Also, when the incident radiation is stopped, there are no photons to transfer the energy to the electrons, and hence the photo emission stops immediately. So here one of the observation we had seen that the photoelectric effect is an instantaneous process. It is successfully explained by using the Einstein's postulate. The next explanation by the Einsteins is given as the electrons that are emitted from the metal surface have different kinetic energies. As when we were discussing the experimental part, we were discussing the observations. So over there we had seen the photoelectric effect will possess with the ejected photoelectrons having different kinetic energies, and there we had taken the maximum value of the kinetic energy. So the same is to be explained by using the Einstein's postulates also. Over here, let us consider the same diagram again. As all the electrons in a solid do not possess the same energy, the electrons may be ejected from varying depth inside the metal surface also. Electrons suffer many collisions before they come out of the metal surface, and hence there will be the loss of their energy. This is one of the reason, that is the Einstein had given that as soon as the photon is to be incident on the material, so it will be collide with the electrons which are situated. It may be at the upper surface of the matter. It may be collide with the electrons which are situated in the interior part of the material. So when the photon is to be interact with such electrons which are situated in the interior part of the material, so these electrons will absorb all the energy given by the photon. But over here, before releasing the metallic surface, some amount of energy of the photon, that is h nu, will be utilized to bring this electron at the upper surface, and hence the part of the energy will be utilized also. Then from the remaining part, the minimum amount of energy will be used to leave the surface, and hence the remaining part of the energy will appear as the kinetic energy of the photoelectrons. So here we can conclude that the electrons which are emitting from the metal surface, those electrons which are situated at the surface of the metal, they will absorb the whole energy of the photon after the collision, and hence directly they are using the part of energy to release the metallic surface, and the maximum kinetic energy will be there with which the electron is emitted. So here, for those electrons which are situated at the upper part of the material having the maximum kinetic energy, then those electrons which are situated in the interior part of the material. Because for such electrons which are situated in the interior part of the material, after absorbing the energy h nu, first of all, some part of the energy will be utilized to bring the electrons at the upper surface, and then it will be utilized as work function and the emitted kinetic energy. So over here, for such electron, there will be the loss of energy takes place, and hence the kinetic energy for all emitted photoelectrons will be different. And the maximum kinetic energy we are getting for such electrons which are situated at the upper part of the material there. That's why in the equation we are considering the maximum value of the kinetic energy, that as the photon is to be incident on the material, the electron will be collide with the photon, all the energy of the photon will be absorbed by the electron, and hence it will be appear as work function, and remaining will be appear as the maximum kinetic energy. Now the next reason was given for the electrons which are emitted with the different kinetic energy by the Einstein, that if the potential V, which is the potential difference between the emitter and collector plate, and the collector plate is at the lower potential, an electron will lose its kinetic energy in overcoming the retarding force. Just try to recall, when the collector plate is to be made at the negative potential, so the electrons are retarding from the, it will be repelled from the collector plate. Okay, the electrons are not reaching to the collector plate, because of which the current is going to be decreases. So over here, if the collector potential will be at lower than that of the emitter, so electron will lose its kinetic energy in overcoming the retarding force. If kinetic energy is not sufficient, the emitted electrons may not reach the collector plate, and hence the photoelectric current will be 0. Next, if the kinetic energy that we are considering over here maximum value, So if the maximum kinetic energy we are taking as the most energetic electron at the emitter surface, and minus V naught we have taken as the stopping potential, then this electron will fail to reach the collector if maximum value of the kinetic energy is less than EV naught. Here we had already discussed that the relationship between the maximum kinetic energy and stopping potential. The maximum kinetic energy we had taken is equal to EV naught. But over here, Einstein had explained that if that maximum kinetic energy is less than EV naught, where E is the electronic charge and EV naught is nothing but the energy needed for the electron to overcome the retarding potential V naught. Because of it, the photocurrent will be reduces there. And if the electron just fails to reach the collector, that means it has lost all its kinetic energy just at the collector. So here we can write down the equation: maximum kinetic energy is equal to EV0, and hence photocurrent becomes exactly 0 at that particular potential, which we are calling as stopping potential. And hence we can say that the stopping potential depends on the incident frequency and the material of the emitter plate, but it does not depend on the incident intensity. It is very clear from the equation that when we are considering kinetic energy, maximum value is equal to EV naught. So this EV naught must be is equal to h nu minus phi 0, and hence over there the stopping potential V naught is linearly depends on the frequency of the incident radiation. Now the next is, as the maximum kinetic energy over here we are considering as EV naught, and the maximum kinetic energy we are taking as per the photoelectric equation as h nu minus phi 0. So the ejected electrons that have the kinetic energy more than EV0, electrons can reach the collector and hence the current is flowing. When the kinetic energy of the electron is less or equal to EV naught, there will be no current flow in the circuit. The photocurrent will become 0 there. And then we are using this situation that when there is no flow of the photocurrent will be takes place at that time, the maximum value of the kinetic energy will be is equal to EV naught. When we are considering this equation in the Einstein's photoelectric equation, then we are obtaining that instead of this maximum kinetic energy, here we have to write it as EV0. It must be is equals to h nu minus phi 0. When we are solving this equation, so we are getting that the value for the stopping potential. Here the value of the stopping potential come to us like h upon E, which is the ratio of the constant, into nu, which is the frequency of the incident radiation, minus phi 0 upon E, where phi 0 is the work function of the material and E is again the constant value charge of the electron. From this equation, we can say that the graph that we have studied earlier, over here in this graph it is very clear that the stopping potential is linearly depends on frequency of incident radiation, and the slope of the straight line that will be depends on the constant value h and E for the whatever material we are using, and the intercept of the line that must be depends on the material through work function, which is to be given here for phi 0 for the material A and phi 0 dash for the material B. And hence we can conclude that the slope of the line is same and is independent of the material of the emitter, but the intercepts are different for different materials. The same thing we had already discussed in the experimental part for the photoelectric effect, and here Einstein's explained the observation based on his concept very clearly. All the above arguments that bring out the fact that the magnitude of the photocurrent depends on the incident intensity through the number of emitted photoelectrons and potential V of the collector, but not on the incident frequency nu, as long as incident frequency is greater than threshold frequency. So all the observations that are related to the experiments on photoelectric effect were satisfactorily explained by the Einstein's hypothesis of existence of photon, or treating light as a bundle of energy. So here part of the chapter dual nature of radiation and matter is completed with photoelectric effect, its experimental setup and observations from the experiment on photoelectric effect, and all necessary proof and explanation for the observations from the experiment on photoelectric effect was given by using Einstein's postulate of quantization of energy and photoelectric equation. The chapter will be proceed further next time. We will see in the next lecture. Thank you.